In part 1 of this lecture, I showed you this method of analyzing a circuit by reducing it to its simplest form and then sort of rebuilding the circuit and finding the currents as you do. And I commented at the time that I don't like that method. I find it fiddly, annoying, it's quite difficult, I think. And so I'm going to show you another method. However, as annoying as I find that method, there are things to learn from it. And one thing that I'm going to point out that we saw is that the equivalent resistance when you have two resistors in parallel is smaller than the resistances of either of the resistors in that parallel resistance. If you were paying close attention, you will have noticed this. When I reduced R2 and RA, which were 300 ohms and 200 ohms, I got an equivalent resistance that I called RB, which turned out to be 120 ohms. And so note we had the 200 ohm and the 300 ohm result in a 120 ohm, which was smaller. And this is always the case. Whenever you have parallel resistances, the equivalent resistance is always smaller. And you can understand why this is so, because if you had the one resistor and now you add the other one in, right? You connect up this new additional resistance in parallel with the first one, you've just given current more paths to flow through, and so you've reduced the resistance because you're making it easy for a larger current to flow. Let's look at another aspect of the intuitions we can develop by thinking about equivalent resistances. Here is a circuit which has light bulbs in it, and let's say these are all identical light bulbs. And I'm going to point out that a light bulb is nothing more than a resistor which is generating so much thermal energy that it gets hot enough that it glows. That's really all a light bulb is. And so that means that the brightness of a light bulb is related to how much current flows through it. It's also related to the voltage across it, right? Because if it's a resistor, then that voltage across it is directly related to the current through it. And so let's think about which of these light bulbs is the brightest. And your knowledge of Kirchhoff's laws lets you now know that all of the current that flows through this one splits at this junction. And so the currents through these light bulbs have to be less than the current through this bulb. And so this bulb, this single bulb here, is the brightest, and each of these are dim. And if they're identical, then the current is going to split evenly. You can't bet on the current splitting evenly at a junction, but if the resistances of the two paths are the same, then it will, and so these will be the same brightness. But now let's think about what happens if we unscrew one of the bulbs. So we unscrew this bulb, we've effectively removed it and made a break in the circuit here. And so it's as if we've just removed this chunk of the circuit entirely. What happens to the brightness of the other bulbs? Remember that changing any part of a circuit tends to change everything else. Well, first of all, we no longer have this current flowing this way. And so all of the current that flows through this first bulb will go on to flow through this second bulb. And so we certainly expect this one to get brighter. However, that's not the end of it, because the voltage that would have been across this pair of resistors has now changed, because we changed the equivalent resistance of this chunk of the circuit. And so, in fact, we made the resistance here less, or greater, by removing that. It was lower when there were two light bulbs, and so we've just increased the resistance, which has increased the resistance of the overall circuit. And so the total current flowing through the battery should reduce, and that means that this bulb is going to get dimmer. Now in the end, this bulb is going to be the same brightness as this bulb, but that happened because this one got brighter and this one got dimmer. So you may have found the way that I analyzed this circuit in the last part of the lecture pretty onerous. And there's no really simple way to do it, but I did tell you I would show you what I think is a better way. And that way is by directly using Kirchhoff's laws. So that's what I'm going to do. Now, to do this, the first thing you have to do is decide which way you think currents go through the resistors, because what you're actually doing when you do that is setting sign conventions that you're going to use in writing down the equations that Kirchhoff's laws tell you. And here it's maybe obvious which way the currents go. It's not always obvious, but it doesn't matter. If you get them wrong, the equations will tell you so in the end, and we'll see that. Not in this one, but in another one I'll show you. So here's I1, I'm saying it goes this way, and I2 should go this way, and I3 and I4 should go this way. And so note, I know that I have 4 unknowns. I've got 4 currents. And so I'll be looking for 4 equations. Well, the first one I can get using this loop. I can write down Kirchhoff's loop law for that, and that'll be an equation. I'll call that loop A. Then I'm going to have this loop. And so I'll call that B, and that'll give me another equation. And then I can use this junction here, and that'll give me a junction law. And I can write down a 4th one. I can write it down right away. I know these two are in series, and so I can just write down I3 equals I4. So there's one of my 4 equations. Now let me use these loops and this junction to get the others. So starting with loop A, I know that I go up a voltage epsilon as I walk through the battery. Then I'm going with the current here, and so I see a voltage drop of I1 R1. And then continuing around, I go through this resistor in the direction of the current, and so again I see a voltage drop of I2 R2, and that gets me back to where I started, and so that's that loop law. And so now for B. Again, I go through the battery, and so I go up epsilon. Then again, I go through resistor 1 with the current. But now I go through each of resistors 3 and 4, again going in the direction of the current. And so there we go. And now I will do the junction. And I know I have I1 coming in, and that has to equal the currents out, which is just I2, and it's just I3, right? Whatever current leaves here is the thing that's going to go through here, and that's I3. I could also write it as I4, because I know I3 equals I4, but whatever, there we go. There are all of my equations, and I can now solve these. Now, I'll say you won't necessarily like this a whole lot better than what I did in the last lecture, but what can you do? So here we go. The method, of course, is that you're going to progressively eliminate variables until you get down to only one unknown. So looking at it, and I have a certain amount of experience of this, I think I'm going to eliminate everything until I get down to I1. And then I'll be able to work back through. So first of all, I can easily get rid of I4 just there. So I'm going to rewrite B as epsilon minus I1 R1 minus I3. And I'm just going to simplify this. This is going to be R3 plus R4. So that's what happens when I plug I3 in for I4 here. And I can now use this to get rid of I3. I just solve for I3, and I'll substitute in for it everywhere else. Okay, and now I'm going to use the equation. So this all came from B. So now I'm going to use A to get rid of I2. And so I'm going to get that I2 is... And now I'm going to substitute these expressions for I2 and I3 into my junction law. And so I get that I1 equals I2, which is epsilon minus I1 R1 over R2 plus and all this. And that probably doesn't look too appealing, but I'll just note that the only unknown in here is now I1, and so I can solve for I1, which I will now do. And that whole mess becomes this. There, and I now have I1. I could plug in all the numbers and have it. And I'm going to leave it at that, because at the point that I now have I1 out of here, I can now come up and I can put I1 in here, which is going to get me I2. And I can then come up here, and I now know I1 and I2, and so I can plug them in and get I3, and I know I3 is I4. And so at that point, I would be done. So the algebra is probably a little nastier than the method of reducing the circuit. However, this method, you don't have to, in the end, you don't have to think as hard. You do your loops, you do your junctions, they give you your equations, and it's all algebra from there. To finish, I'm just going to show you why using the method of reducing a circuit to a simpler circuit sometimes just totally fails, which is the other reason I prefer directly using Kirchhoff's laws. Look at a circuit like this, and think about how you would reduce it. Well, R1 is not in series with either R2 or R3 because there's a junction in between them. R2 and R3 are not in parallel because going from this end of R2 to this end of R3, we have to pass through this battery. And we have no way of combining a resistor and a battery. Now, if you take a more advanced course on circuits, you'll learn something called Thevenin's theorem that would let you reduce this, but we can't get into it that far. So here you can't reduce this circuit at all. And in fact, you really commonly come across circuits that you cannot reduce, at which point you have no choice but to directly apply Kirchhoff's laws to try and analyze them.